Herkese iyi akşamlar. Bu akşam TÜBİTAK Temel Bilimler Araştırma Enstitüsü'nün Kuantum Bilimi ve Teknoloji Seminer serisi kapsamında bir güzel bölüm daha gerçekleştirmek üzere bir araya gelmiş bulunmaktayız. Kuantum dediğimiz zaman aklımıza ilk gelen kuantum mekaniğidir. Kuantum mekaniği 20. yüzyılın başlarında ortaya konulan ve kuantumu anlatan devrimsel bir fizik teorisidir. Geçen yüzyılda ve günümüzde geliştirilen tüm yüksek teknolojilerin zemininde kuantum mekaniği çerçevesinde ortaya konulan çığır açıcı fikirler ve yöntemler yatmaktadır. Kuantum mekaniği, diğer doğa bilimleri ve uygulamalı bilim alanları için bir anlamda işletim sistemi rolü oynamakta, farklı bilim dalları arasında bilgi akışına yol açmakta, bir daldaki gelişmelerin diğer dallara da ışık tutmasını sağlamaktadır. Bugün gelinen noktada kuantum mekaniği fiziksel dünyayı mükemmel bir hassasiyetle tasvir etmekteyken, bir zamanlar kuantum mekaniği çerçevesinde sadece paradokslar bağlamında tartışılan kuantum süperpozisyon, kuantum dolanıklık, kuantum teleportasyon ve benzeri spesifik olayların, yapıların kullanımı ve tutarlı kontrolü yeni bir kuantum devrimine yol açmaktadır. Bu kapsamda son zamanlarda yapılan deneylerle, örneğin şimdiye kadar erişilmeyen hesaplamaların kuantum bilgisayar donanımı ile gerçekleştirilmesi ve benzeri kritik bir eşiğe yaklaşılmaktadır. Bugün bütün bunları son derece değerli ve dünyaca ünlü bir bilim insanı Profesör Doktor İrfan Siddiqi'den Kaliforniya Üniversitesi Berkeley, Süperiletken Kuantum Bilgi İşleme Umudu başlıklı bir konuşma kapsamında dinleyeceğiz. Ben de bu vesileyle hepinizi saygı ve sevgiyle selamlıyorum. Seminerimiz İngilizce gerçekleştirilecektir. Bu nedenle İngilizce devam edeceğim. Dear Professor Irfan Siddiqi, dear participants, dear colleagues and friends, a very warm hello everyone. It is my distinct pleasure that this evening we have another wonderful episode of the inspiring online Quantum Science and Technology Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences. We organize these seminars for national and international audiences with the participation of distinguished scientists and great speakers of the world. It is also my sincere pleasure that I have the privilege and honor of introducing our tonight's very special speaker, world-class expert of quantum science and technology, Professor Irfan Siddiqi from the University of California, Berkeley. He has kindly agreed to join us for this seminar, and he's going to give a great talk, The Promise of Superconducting Quantum Information Processing. Irfan Siddiqi is an American physicist and currently a professor of physics at the University of California, Berkeley, and a faculty scientist at Lawrence Berkeley National Laboratory, LBNE. He currently is the director of the Quantum Nanoelectronics Laboratory at University of California, Berkeley, and the Advanced Quantum Testbed at LBNL. Siddiqi is known for groundbreaking contributions to the fields of superconducting quantum circuits, including dispersive single-shot readout of superconducting quantum bits, quantum feedback, observation of single quantum trajectories, and near-quantum limited microwave frequency amplification. Professor Irfan Siddiqi is a fellow American Physical Society and a recipient of its George Valley Prize in 2006. He received the University of California, Berkeley Distinguished Teaching Award in 2016. He is a 2021, that is this year, recipient of Joseph Getzley Award for Advances in Measurement Science. Siddiqi received his AB in chemistry and physics from Harvard University in 1997 and a PhD in applied physics from Yale University in 2002. With this, I want to invite Professor Irfan Siddiqi to the stage to begin his talk. Irfan, good morning. We are very happy to have you with us. Please begin your talk.
Good morning, Professor Ali Ikram. It is a tremendous pleasure and honor for me to be here. And I want to thank you for the kind invitation, the kind words of introduction, and of course, the very warm welcome and introduction that you gave. I only got a small fraction. My Turkish is not good enough to get all of it, but thank you for that. And I see on the line, Professor Ali Gencer is also here. So he has invited me in the past kindly to very wonderful conferences in Turkey. So I hope that everyone enjoys this brief presentation today on quantum mechanics, and in particular, the transformation of quantum mechanics from a philosophical subject, as you mentioned, paradoxes in your introduction, going from this type of thought experiment really to an engineering resource. The structure of the talk, and I will go ahead and share my slides now so you can see them. Okay, is this visible now properly?
Yeah, it's perfect.
Okay, excellent. The structure of the talk, I was assuming, is going to be a broad audience. So there's a little bit of philosophy, a little bit of physics, a little bit of engineering, and a little bit of a sense of where the field is going. So in a nutshell, I hope to cover a very broad subject in about 45 minutes here. And then I'm, of course, happy to take a healthy Q&A period after that. So let me start by first thanking the people that actually do all the hard work in the group. So there are many students and postdocs and scientists in our effort. They are listed here in the different topics that they work on. In particular, we have a team that does fabrication of these qubits. There are teams that look at their operation within a quantum computer setting as we go ahead and put that together. And all of these teams work together. The rough breakdown, if you see, is shown there between scientific staff, postdocs, and graduate students in the lab. So a big thank you to them. I wanted to start off with this picture. This is a picture from the Amelia Seagrave archive showing Einstein and Bohr walking together in 1930. And this particular photograph is really sort of dated around the time where they had these very famous Einstein-Bohr debates, right? They were really going back and forth about a title which I think is very nicely illustrated in this book. It says Einstein, Bohr, and the Great Debate About the Nature of Reality, right? And quantum mechanics was a very, very interesting theory. If you look at the evolution of scientific theories, it was, in my mind, one of the very first times that we said our observations of the world around us reflect only some aspects of a much more complex hidden reality. And this is really a change of mentality. Typically, physicists are looking at things they can observe. You write down some mathematics to observe that. And if you are unable to write the mathematics of that, it's because your observational tools are not good enough. It's not because of the fact that you will never be able to measure them. And quantum mechanics tells us there is a wave function that you cannot directly measure. And it describes some greater complexity. You can measure some pieces of this only at one time. And that's really a radical change in thought. And the idea is, well, why do we actually need that? Maybe it's wrong, right? Maybe that's not the right way to think about the world. And what's amazing is that this underlying structure is absolutely necessary to talk about, for example, teleportation or other even very basic phenomena around the physical world around us. Without this underlying structure, it does not work, even at the scale of the universe. Now, of course, there may be other theories, but at the moment, there are no violations of quantum mechanics. So in some certain domain, it seems to work extremely well. So this debate, of course, went on for about 100 years, a little bit less, because we really did not have the tools to manipulate this underlying structure or entanglement. And I think this is what makes this particular time period in physics extremely interesting, that we are entering an era where we can finally use the quantum nature of matter as an engineering resource, right? And that's really the subject of the talk today. I wanted to mention some words about what are the challenges in doing that, what are some applications that we envision at the current moment for this entanglement engineering, if you like. So the talk is structured in the following way. I will give a very brief sort of contemporary introduction to quantum computing and simulation, then focusing a bit on my own subject, which is superconducting qubits. And then I will take a little bit of a deeper dive in terms of noise processes or decoherence processes, which are really a fundamental, not a fundamental, but a major limit at the moment to expanding quantum information and quantum computers, and say how we can play some interesting tricks by looking at that noise structure to actually enable simulations of quantum chemistry and simulations of nuclear dynamics. So I'm starting off with a little bit of a broad introduction and then focusing on, very likely, on two applications that we have recently executed. So with that, let me start with the introduction to quantum computing and simulation. So the world around us, again, as was mentioned in the introduction, in the dunya, this is all quantum, but we don't always see these quantum effects in the way that we are trying to harness them at the moment. So let me start with this image. So one of the most quantum mechanical things around us that we interact with is an MRI scanner. So if you've hurt yourself, like many of us, and required an MRI scan, you go into the magnet, the bore of this large magnet, and then image is produced. And what's happening there typically is that you have water molecules, and these have two hydrogens, and they have a nuclear spin, which points up or down. And the question is, which way is up and which way is down, right? And the point is that the up and down is determined by the direction of the magnet that you apply, the magnetic field. So if you apply a magnetic field in the vertical direction, you will always measure up or down. However, we know this underlying structure of quantum mechanics tells you that you can have a more complicated state. You can have a superposition of spin sideways, shown in green. And if your measurement apparatus only measures up or down, there's no way to characterize spin sideways. The only way you can talk about spin sideways is to say it's a mixture, 50-50 of up and down, reflected in the fact that if you make a measurement, for example, in this block sphere, if up and down are represented by 0 and 1, and the green is on the equator, if you would measure such a state, half of the time you measure up and half of the time you measure down, right? And this is quantum mechanics 101. So the takeaway message here is that quantum systems can exist in many different configurations, even if you cannot observe all of them. So why is MRI not a quantum computer immediately? Well, what is typically happening is you are not measuring one water molecule. You are measuring an ensemble property together of a lot of these water molecules. And the endeavor at hand in quantum computing is to control and to measure every element of your quantum ensemble. So every water molecule in the flesh would have to be measured to make a quantum computer. And that illustrates the challenge of the problem. Many of these systems are small physically, they're difficult to couple to, and of course, decoherence, as we'll talk about, is also challenging. So what if we were to make a computer based on this kind of NMR principle? How would we do it? So let's build a computer one spin at a time. We take each one of those molecules, as I talked about. And unlike magnetic resonance imaging, which measures average properties of a group of spins, we need to address them individually. So let's put them on a grid. Okay, so I've put here some spins. You can imagine these are the individual molecules. And again, I have oriented my measurement up or down. So if you were to measure them independently, they would be pointing up or down. And here is a random configuration that I've put there. So now what we're going to do is let's talk about this one spin that I'm pointing to, which is pointing up. Okay. If you don't observe it, then as we said, it can be in a much more complicated state, as our host said, a superposition of up and down. And we can express that mathematically by two numbers, A and B, right? So A tells you the fraction or probability of being up, or A squared, and B tells you the probability of being down. So the most general state of that one square, can you see my mouse as well?
Yeah.
Yeah, so the most general state is here, up plus down. But what about now I also cover up its neighbor, right? So this one now is C plus D, up and down, another set of numbers. And now the third element of this is, let's imagine you couple them together. So somehow in their life history, they talk to each other, right? So the states that you can get now are more complicated, right? So if you couple these two together, one of the most simplest states you can make is simply just a product, right? If you couple neighbors. So you take A plus B and you multiply by C times D, and you will get this state, right? And that corresponds to four combinations, right? Up, up, up, down, down, up, and down, down, right? With these four numbers. But what's interesting is that you're missing a very simple combination, right? In this product state, you are missing the superposition of up, up, and down, down, right? And in fact, there is no way to write from this product state, this state. And you can see the very simple mathematical exercise. If I want to drop, these two middle terms, if I set A equals to 0, then I have a problem. I lose the first term, right? And if I want to drop this term, I set D equal to 0, let's say, or I drop here D, then I drop this term. So this is a very simple example of how there are states which are in fact entangled that are not describable in an independent or product-like description. You cannot describe this state as somehow simply being this red state plus the blue state. It is really a unique state, an entangled state. And that complexity of states, that number of entangled states grows as 2 to the power n, right? And it's much larger than 2 times n, certainly for a large number of qubits, right? And in fact, if you have 300 qubits, 2 to the power 300 is more than the number of particles in the known universe, right? So you start to see how quantum complexity very rapidly enters into some kind of information science, saying that if I were to really build such an array, if I were able to control this coherence and entanglement, I would have a very complex state of matter. And then the rest of the game is how to stabilize such a state. How do you read out such a state? How do you program such a state into a computer? And those are very difficult questions and exciting ones that are at the heart of quantum information processing. So with that, one could, of course, build a computer out of molecules, and there have been many efforts in NMR. And in fact, really any physical system where quantum mechanics is observed is perfectly fine to build a quantum computer. What I would like to highlight here are a few systems that are commonly used. So they range really from, if you would like, closed quantum systems or systems that don't interact with their environment very strongly. So photons are a great example of that. A photon is a very stable quantum entity, right? You can create coherent superpositions of it. It will have a very long lifetime. The quantum mechanics will not go away. The challenge is the entanglement step that I showed you, where you wanted different photons or different quantum elements to get entangled. This is hard for this system because naturally it likes to be isolated. On the other spectrum, you can move to things which are more interactive, whether they be trapped ions, so individual ions, let's say of calcium or some other species. And you can even trap neutral atoms, let's say rubidium atoms. So that's another very interesting platform and promising platform for quantum information science. You can talk about individual electrons. So this can be like your conventional silicon electronics, where you have shrunk the scale so that you are dealing with individual electrons in a transistor, say. Okay. And the challenge, of course, in such systems is a little bit of the opposite. The electron likes to interact with everything. So it's very hard to isolate individual electrons. So just giving you a sample that quantum mechanics works in many different limits, certain limits where the interaction is strong with the environment and certain limits where the interaction is weak. But there is no free lunch. There is no free donor to be had here, right? Because if the interaction is strong, that means the decoherence is strong. If the interaction is weak, it means it's hard to do the control operations in that. And what I've shown on the bottom here are two different setups. These are really mesoscopic or microscopic systems. So I work with superconducting qubits. So these structures, as we will talk about, actually have finite scale. They are not on the scale of an individual atom or an electron. They are lithographically defined at the scale of tens of nanometers, hundreds of nanometers. However, when you cool them down to very low temperatures, then they behave collectively like a plasma, like 1 degree of freedom, right? So in some sense, you are getting the benefit of having a simple system like an electron or 1 degree of freedom, but you are able to manipulate it with a more macroscopic object. I can pass current through this, I can pass voltage through this. The challenge and the price to pay, of course, is that as you make the system bigger, it again has many ways to couple to the environment. So any kind of amorphous surfaces or bad interfaces or noise coming in from the outside environment, all of these things are things that I have to work on. And finally, I have this technology, which I think is, of course, very, very interesting and promising, but it is very difficult to realize, which is a system with topological protection. So we can talk about this a little bit later, but one of the ideas here is to encode information in such a way that the environment, in fact, cannot get at it. And I can give you a very simple example of that. In electronic states, if you have the state of an atom, you have the ground state and excited state. So any photon can couple those two states. In a topological system, you can think about like the poets of old age used to do. They used to write their poems in knots on strings. So you can imagine you have two strings and they are either separated or twisted, right? That can be the 0 or 1. And if you twist the string, you see you can bend it any way. You cannot take out the knot. It's very hard to take out the knot in your shoelaces, right? So that's a very robust way to save information. But again, the challenge then is how do you then actually perform logic operations on this? So again, no free lunch in quantum mechanics. You still have this divide of protecting quantum information, but at the same time also using it as an engineering resource. And again, for MRI, to give you that example, you see you only had to deal with one of the challenges there, right? Which was in fact to deal with the ensemble. You did not measure the individual pieces. And that's why MRI is a very different problem than the quantum control problem. But nonetheless, progress has been absolutely tremendous in this field, right? And over the last 2 decades, so many things have happened. In particular, I wanted to highlight this one experiment that I would imagine most people have seen in the news. This is a demonstration by the Google Quantum Information Group of something called quantum supremacy. And the idea here is that with, let's say, of order 50 or 53 or some more numbers of qubits, you can start to build a state which is no longer efficiently described by a classical computer. Right? And we will talk a little bit about that when we talk about chemistry in a few slides, but this is quite amazing, right? We are now starting to able to put together, albeit noisy, albeit not powerful enough, quantum ensembles in machines. You can start to enter the limit where their description is not possible using classical computers. And there's also then a very interesting question, then how do you test your quantum computer? There is no other computer to test it with, right? And benchmark it. So they're very interesting regime of such machines. So with that, if you had a quantum computer, what would you do with it, right? So if you forgive me, I've taken a little bit of a finance or business tact here, taking a slide from this report which has come out recently, and I wanted to put the reference here if folks wanted to sort of a very high level introduction into the business aspect or industrial aspect of quantum computing or the application aspect. This report by the Boston Computing Consulting Group is quite nice. So the basic idea up here is that the mathematics of matrices is something which requires quite a lot of computational resource. You remember, and when you were a student, probably you were trying to diagonalize matrices by some kind of elimination method or some kind of determinant method. If your matrix has like 1 million elements, that's a really hard task, right, to do even for classical computers. And the scaling of the challenges associated with that kind of matrix mathematics is hard to do. So if you think about how to deal with matrices and how to actually solve matrix equations, then quantum mechanics gives you some interesting ways to do this, okay? And some clever ways to deal with this parallel ensemble in an efficient fashion. You don't have to deal with those differential equations one at a time. You can try to deal with them in an array. And if you are able to do this, then there is at least 4 categories of applications that are listed here that are interesting. So you can try to simulate complex systems. And again, I'll give you a few examples of this. But in terms of drug discovery, fluid dynamics, design of catalysts, solar energy processes where you want to model photosynthesis synthetically, and of course in finance, if you want to look at a portfolio or insurance, how risky is it to do a certain investment? These require lots of equations to be solved together, and quantum mechanics may help with that. Similarly, with optimization, if you need to solve the minimum of a function that has many dimensions, that requires lots of equations. Machine learning, no different, right? If you are looking at vector support machines or principal component analysis and so on and so forth, all of these applications require solving matrices. And again, there is also the uniqueness of entanglement, meaning that when you make a measurement, you perturb a quantum system, and that's useful for cryptography. And this was appreciated very early on in the field. So this gives you a sense of, the application space is big. There are real world applications that may come out of this. I want to focus on this simulation piece, right? And in some sense, this is really what Feynman was originally talking about, saying that quantum systems are complex, but nonetheless, they interact. And let me sort of give you a physical example of this. If I take 50 atoms and I arrange them some way, they know what the lowest energy arrangement is, right? If they are allowed to move, they will move and find that arrangement. For me, that's very difficult to write down on a classical computer, right? I would try to write down the Hamiltonian. And if you remember from your quantum mechanics classes, after helium, life gets already very hard with 2 particles. So if you try to write down 50 or 100 or 1 million atoms, very, very hard, right? Impossible to write down those equations. But nonetheless, the particles themselves know how to arrange themselves. And that's really the principle of this quantum simulation. Can I encode a problem in quantum degrees of freedom and let them do their interaction, and I just read out the answer? So for example, if I wanted to figure out the energy of a certain catalyst that has all of these pieces, I would just go ahead and place those physical pieces, right? And measure the energy. So this is the idea of this kind of physical simulation. And what I want to show you, because I think this will help not only with this talk, but also help you digest a little bit of what is in the news, right? How many qubits do we have? How many qubits do you need, to do something meaningful? Well, the qubit number axis by itself is not sufficient to describe these problems, because you have to sort of describe how good is the qubit, right? So for example, how long can it live? And in particular, what is the probability of error, right? And error is something in classical computers we have completely ignored because the encoding is so robust, right? If your classical computer has 1 bit at 0 volts and 1 bit at 5 volts, you will never make a mistake, right? Reading 5 volts for 0 volts. And typically the only mistakes you have are from cosmic rays. They're very, very rare, right? So no error correction is applied, typically to classical routines. Quantum mechanics, not the same, right? Quantum mechanics, you can have the atom flip, emit a photon, and the error rate is typically very high. Now, notice you don't get that for free in classical systems. When you encode in such a robust state, first of all, there is no quantum mechanics. And number two, the energy cooling requirements are huge, right? So if you have a classical server farm, you require tons of energy to cool it. In fact, you try to put it in cold countries in mountains, right? Where you get cooling for free. Whereas in quantum mechanics, the energy dissipation is very small, right? Going almost to zero, but the error rate, of course, is not zero in that case. So I've put a second axis here. This axis here tells you the probability of an error. 1 would be horrible. That means every time you try to run a bit flip, you get an error. And of course, something like 10 minus 4, 5, 6 would be outstanding, right? So these two axes show you number of qubits going up by 5 orders of magnitude and the error rate going down by some 8 orders of magnitude. So the current state of the art is in this little triangle, which is here. This is what we have for our qubits. You have somewhere between 1 and 100 qubits. And at best, you can get somewhere around 10 minus 3 error rate. Right? And typically, the more qubits you have, the higher the error rate. What you would like to have in the future is some kind of error-corrected universal quantum machine. This is basically the quantum equivalent of your PC. Right? This will do everything you want. And you can see that is some orders of magnitude away, even on this log-log plot, telling you that this is a long-term scientific investment. The boundary, which is interesting here, is this classical simulation limit. So I'm telling you, like this Google problem, how many qubits do you need where it becomes not reasonable to simulate them classically? For a meaningful problem, that's somewhere around here. Okay? And so the idea here is that in this regime, we have currently 10 to 100 qubits, not a lot of error correction. And we are looking at algorithms which are hybrid. And I'll give you examples of these. And the idea is somehow to push across in this boundary in some favorable way. Okay, so the basic science, hopefully to motivate the generations of folks looking into this, because it is a hard problem. The basic science is still very open, right? We are still very much open to discussion of what the magic qubit is. What is the right system to encode this quantum information? How do you correct for errors? And how do you interface quantum data with classical data? Because after all, you don't read out entanglement directly. And how do you actually have an efficient exchange of data? And what are the most important problems? I personally don't feel we have found the most important problems. Think about the vacuum tube in the 50s or so, or 60s, right? What is the relationship of the vacuum tube to Facebook today? Right? We have not mapped out, what quantum may look like in 30, 40 years. So we need to keep an open mind for that. And also when we design our algorithms. Okay, so that was my brief introduction into a little bit of what is the premise, the promise, and the technology of quantum computing. And we'll go a little bit more now into the science of one of these platforms, in particular, the one on superconducting qubits. So the science starts here. After all, quantum mechanics was the study of atoms and photons, right? This is how the science started, looking at black body radiation, the emission from gases, so on and so forth. And as I mentioned, both of these objects have large coherence because they do not couple to the environment. You can put it very strongly. You can put an atom in the excited state, it will stay there for a long period of time, right? It will emit a photon. You can measure that photon. You can keep the states of photons, so on and so forth. But electrical circuits are just as quantum mechanical. as this photon. And the basic mapping really starts with the harmonic oscillator, right? So you learn about the harmonic oscillator in quantum physics. This is a system that has a parabolic energy surface, and each one of the levels are equally spaced in a harmonic oscillator by frequency h bar omega, right? And omega is the frequency of this oscillator. This oscillator, if you have a mechanical system, can be just a mass on a spring, which is moving. If you have an electrical circuit, then this is, for example, an LC circuit, right? And you can see the capacitor really formally will be like the mass, and the inductor will be like the spring. And the two coordinates that you have are not position and momentum, but rather the charge on the capacitor and the flux, right, through the inductor. And the charge and the flux, they obey this canonical relation, just like X and P. In quantum mechanics, they give you this IH bar canonical relation. So those are the quantum degrees of freedom in this electrical circuit. And how do you couple to this flux and this charge? You couple to them by a current and a voltage. So that is the formal recipe, if you like, mathematically, how a voltage and a current can control something which can be written in terms of A and A dagger, right? Formally in terms of quantum mechanics. Why do we have to go cold? This depends on the frequency of operation. So if you are working in this 1 gigahertz or few gigahertz range, then the level spacing will be of order 50 millikelvin, right? So if you would like to be at a temperature where you are not thermally populating all these states, we need to be significantly below 50 millikelvin, and that drives the need for dilution refrigerators, say, going down to 10 millikelvin. Okay. So this is a perfectly good quantum system. However, there are some limitations if you would like to make a qubit out of this. The first limitation is that you cannot address in a pure harmonic or pure linear system any two levels, right, independently. All of these levels are spaced by the same amount. So if I put in a photon, I would excite the ground state to the first one. If I put another photon in, then it's equally likely to go to the second state or back to the ground state, because they are all separated by the same energy space. If you would like to make a bit, you would need some nonlinearity so that the level spacing is not uniform. So you may remember for some quantum mechanics class, this harmonic oscillator is very magical, right? All the states are equal. If your potential surface was a box, right, like an atom or a hydrogen atom potential, then those levels are no longer equal. So we have to introduce nonlinearity into the circuit. And the way we do this is we keep the capacitor the same, but we replace, in fact, the capacitor is the same, we replace the inductor by a tunneling junction. So this is the magic element. So these are two superconducting electrodes that are separated by a tunnel barrier, okay? So Cooper pairs can tunnel across this element. In essence, it's a nonlinear inductor. And it's nonlinear in the sense that the inductance changes depending on the current that you pass through it. So the harmonic oscillator, just like a pendulum, the frequency does not change for a simple pendulum depending on the amplitude. However, for a physical pendulum, the frequency does change, right? Because you have the sine term coming in. That's exactly what's happening in this inductor. There is a sine term that makes it nonlinear. And in fact, this is the heart of all superconducting qubits. They have a tunnel junction, which gives you the nonlinearity, and in essence gives you a weak anharmonicity to this level structure. So typically, this kind of junction shown here, this is aluminum metal with aluminum oxide in between. The size scale you can see is 500 nanometers. For this type of junction, you will get, let's say, a frequency in the 1 to 10 gigahertz range. The anharmonicity, meaning the difference between the red and the blue and the green, is few hundred megahertz. Okay, so you have basically the next level being not 1 gigahertz, but maybe 750 megahertz, so on and so forth. And that anharmonicity is what allows us to operate this as a qubit. Okay, so how do you read it out, right? That's also an interesting problem. I can go ahead and make this circuit. If it sits there, then no information is exchanged with it. Equally hard problem is how to get photons in and out of this system. It is very convenient these days to put such a circuit inside a microwave cavity. Okay? And the physics of this cavity is shown here by a Hamiltonian called the Jaynes-Cummings Hamiltonian. So what happens when you put such a circuit, think of it as a dipole or an atom. When you put this kind of dipole structure in a cavity, you pull the cavity frequency depending on whether the spin is pointing up or down. That's it. So if you like, this is the quantum version of a classical dielectric. If you have a capacitor and you put a piece of plastic in it, you will pull the energy. So what you're doing here is you're putting in a dielectric, which depends on whether it points up or down, right? It's a dipole. And mathematically, for those that are of mathematics aficionados, what is shown here is the Jaynes-Cummings Hamiltonian. It shows you h bar omega sigma z. This is a two-level system. Sigma z is a polymatrix that points only up or down. So this gives you the two-level system. A dagger A plus a half gives you the resonator. And then there is a term which shows this G, which shows the coupling between this dipole and the cavity. And there's a term here, A dagger sigma minus A sigma plus, telling you how you can exchange one excitation from the spin to the cavity and back and forth, right? So it's a very simple linear exchange term. And if you work in the limit where these two frequencies are detuned, what you will see is very clearly here that omega r, the frequency of the resonator, is changed by sigma z, by the state of the qubit. So physically speaking, it means that if you probe the transmission of this cavity by microwaves, you will see a frequency shift, depending on whether the qubit is in 0 or 1. So that's it. That's the principle of readout of these qubits. And physically speaking, what happens is you take your circuit, you put it in some cavity, whether it's a physical cavity or on chip, you excite with microwaves, okay? And if you look at the phase of the reflected electrical signal, you will see a large phase shift, showing the difference between 0 and 1, okay? And you can plot this, if you're an optics person, you can plot this on a kind of phasor diagram for coherent states, and you can see the coherent states which correspond to the red and blue states are different, and you can read them out. So just a little bit of technical background for the experimentalists. Going from the Jaynes-Cummings for the theorists to the experimentalists here, you would just excite your circuit with, let's say, 1 microwave photon, which is hard, but you excite with 1 microwave photon and you look at the phase difference outside. Okay. And that's how you map a voltage into a quantum state. What goes wrong in this process? This looks great, right? We can make this circuit, you have 2 levels, so on and so forth. Looks like you can build a quantum computer tomorrow. Unfortunately, not so easy, because what happens is the lifetime in these states is typically very short unless you do a lot of engineering. So let me sort of illustrate what can go wrong. Start with me, please, in the upper left. So this is the usual representation in the Bloch sphere. As we said, pure 0, pure 1, pure spin up, pure spin down. These are the 2 poles of this sphere. Any superposition, psi, is written in terms of 2 numbers. We had written A and B, here is alpha and beta, of 0 and 1. This is basically a point on this sphere, right? It's a point anywhere on the sphere. So things that can go wrong, first of all, you can have what is called longitudinal relaxation or bit flips. So you are in the up state and you go to the down state and you release a photon. Okay, so that's spontaneous emission, if you like. You can also have dephasing. Let's imagine you were on the equator, right? And you sort of move around left or right, that's dephasing. And then of course you can have the combination of these 2 things, right? And that's called these 2 times together are the decoherence times T1 and T2. The rates here are gamma 1, gamma 2 that are seen in quantum systems, and they are reminiscent of the numbers in NMR. So in this chip that I'm showing you, it has 8 qubits. I'll show you a picture in a moment. The lifetimes on average are of order 100 microseconds. So that actually represents quite some decades worth of work of starting from 1 nanosecond and going up to 100 microseconds. You have to compare that time with something. Is 100 microseconds fast or slow? This depends on how fast you can do logic on these circuits. So the logic, as you can think about for qubits, is rather related to rotations. So for a single qubit, I showed you the state on the Bloch sphere. What you want to do is flip it, rotate it, and you can think about an X gate where you rotate by 90 degrees here, 90 degrees here, so on and so forth. Those are single qubit rotations. And in our system, we are able to do these rotations with the fidelity of 3 nines or better, right? 99.9%. Think back to the graph I showed you. With the quality that you need for high quality simulation, 10 minus 4, 10 minus 5, we have 10 minus 3. For 2 qubits, you can imagine this picture that I showed you with NMR, with the coupling, with the entangled state, so on and so forth. And with 2 qubits, the matrix is a 4x4 matrix, right? And typically you can do a controlled NOT gate or a minus gate. So these are different ways to actually have the quantum equivalent of a XOR or some other classical gate. These are harder. They are still in good fidelity for us, 2 nines, a little bit better than 2 nines. We can even do logic on 3 qubits. And again, the timing for these gates to be compared with this microsecond or 100 microsecond coherence is that we can flip 1 qubit in 30 nanoseconds. We can do single qubit gates in about 60 nanoseconds, any one of them. And in fact, the 2 qubit gates take a bit longer, about 200 nanoseconds. So that gives you a background into the superconducting circuits and sort of the noise properties that are there. What I would like to talk about now is, can you do something about this noise? Is it always going to destroy the system? Are there tricks that you can play? There's a lot of interesting physics in thinking about the noise processes in these qubits. I showed you a few slides ago these different longitudinal relaxation, the bit flip, and so on and so forth. I can write them down now in actual matrices. And it's actually interesting to see what these matrices look like and how they concatenate. If I have noise which just loses information to the environment, we call this depolarizing noise. What's happening here is your pure quantum state on the surface is shrinking because you no longer have this very simple superposition. And the way you write that as a decoherence matrix or as a noise matrix is that you take away some population P along the 3 axes. So this is called depolarizing noise. Dephasing is basically loss of information when you're on the equator. So you see the X and Y has this. And interestingly, there is an error which turns out to be very common here. And this is the one I'm going to focus on. This is a coherent, this is a coherent error. So the idea here is I want to produce this gray state. I want to do a rotation, right? By 30 degrees or something. And my control electronics are not good enough. I rotate by 31 degrees, right? That's not a decoherence error. Information is not lost. I just messed up, right? By a few degrees. So you can parameterize this error by an arbitrary rotation along some axis, pointing along the direction here by theta. And it turns out these errors are very bad. These coherent errors, in fact, accumulate very badly in your system. And I'm going to show you a way to sort of turn these coherent errors into stochastic errors or into depolarizing noise. So coherent errors result in an under rotation or over rotation. The coherence is not lost. I still have a state alpha plus beta. It's just alpha and beta of 0 and 1 are not the ones that I expected. What's really bad about them is the way they accumulate. So let's imagine I have one over rotation, then the next one, then the next one. You may get lucky and they cancel, or you may get very unlucky where they all add up in the wrong direction, right? So very unpredictable where these errors go. And they, in fact, really are correlated with each other. So they have a quadratic effect at the end of the day. Whereas stochastic errors, which is just a random noise, they don't accumulate the same way and have a linear impact on your system, and they scale a lot more friendly. So the question is, can you tailor noise to take coherent errors into stochastic ones? And is that useful for actually running a more complicated quantum algorithm? So if you have these stochastic errors, you can think about, I showed you the matrix, the error term is 1 minus P. If you raise that to the power n, this is the linear scale. It goes as n times P for n gates. If I have coherent errors, then you have to take the product of these n rotations, and you end up with something that scales as n squared. So you see immediately that the scaling in worst case is different. Moreover, the impact on your gate fidelity is also bad. If you only think about one type of error, you can really mess up the scaling fidelity that you get from these gates, because as I said, they don't accumulate in some simple way. Moreover, the error rates that you need to reach that fault, this is for some experts in the audience, that little dashed line that I showed you where fault tolerance was, the threshold that I showed you also scales differently for these two types of errors. So that's also important. So what's the simple way of getting rid of this error? This is a quantum circuit diagram. What they typically show you is these lines represent the history or pulse sequence of a qubit. So one qubit is here, second qubit is here, next one is here. These boxes represent gates. This is an X rotation only on one qubit. This is a gate which makes a superposition state, so on and so forth. Elements which couple two lines are 2 qubit gates. This is a controlled NOT gate. So you can see these are single qubit rotations, 2 qubit, single qubit, 2 qubit. The idea is let me put some randomizing gates in between. So between these operations, I put a random rotation, okay? And what that random rotation does, it breaks this concatenation of coherent errors. And the way I put this rotation in is I do a Y rotation and then I undo it, right? So that way the overall circuit is not affected. So I put in some random effect and I undo it. And then when I recompile the circuit, you see it's the same number of operations. All I've done is change randomly these orientations. So how does that physically work? Think about, let's say, this target state. I miss it, right? And I do this many times, right? I miss it many times. So this is, in fact, the distribution of states that I get. The average of that is better. It points along the axis, but the length is reduced. So I can compare that state to one iteration here. And this is real data. So I'm trying to hit, for example, this blue state. And you see on average of many iterations with this noise correction, the resultant state is better. I've changed this noise, which was coherent and moving me on the surface of the sphere, to a reduction of the vector, right? Which is basically a depolarizing noise. So you can ask yourself the question, if you are stuck in the forest and have a compass, do you care about which way the compass needle points, or do you care about the length of the needle, right? Typically, you care more about which way the compass needle points. And that's really what's happening in quantum here. The blue state is, the orange state is better aligned to the black, even though it's a little bit shorter. Okay. So if I go ahead and I run now C0 gates, what I'm showing here on the vertical axis is the probability of incorrect solution. 0 would be great, 50% incorrect is already bad. And you see bear is in blue, right? Without this randomization, orange is shown here. Even if I'm running 14, 15 C0 gates, which starts to get to be a lot of gates, I see a significant improvement by using this randomization. So in the last few minutes, I want to give you two examples, right? Is this practically useful? Or is it just a mathematical trick that I'm showing you? We tried to run some chemistry simulation. So to give you a little bit of background, this is the number of atoms that you can simulate in a chemistry simulation by the year. And you see it goes back to 2003. So there's not a lot of progress in these methods. For example, the exact treatment of the Schrodinger equation, you are limited to less than 10 atoms, right? That's how hard the problem is. And the reason typically is that you run out of memory. You need petabytes of memory, which even your most powerful supercomputers do not have. And it's an unfriendly scaling. Even if you have this memory, one more atom will make it so much more difficult. So is there a problem of interest that can be solved perhaps by a quantum computer? Think about this process for building ammonia. So in ammonia, you're combining nitrogen and hydrogen to make ammonia for fertilizer. This process, known as the Haber-Bosch process, happens at high temperature, high pressure. This takes 1 to 2% of all the energy on Earth to produce this fertilizer. That's a lot of energy for doing this. However, plants do this naturally at 25 bacteria at 25 centigrade, 1 atmosphere, and we have no way to calculate this catalyst. Classically, it's beyond reach, as I showed you. Quantum mechanically, if you had a reasonable number of qubits, you could solve this problem. And in fact, here's one algorithm where we start by looking at, this is the quantum evolution of the ground state. We go to imaginary time, and what you see is then you can go ahead and calculate by quantum mechanical means the individual operators. The process is hybrid. So you go ahead and have a quantum circuit, you map your problem. And again, I'm leaving these slides so that people may watch them on playback or look at papers, not to go through them, but just to show you how the algorithm works, right? You start with a quantum circuit, you measure the expectation values, you measure the quantum configuration, and then you change their position, right? And find the minimum of the energy here. So in this case, we did that for the transverse field Ising model, right? And you can see we can start to get in this very common model of spins, the proper energy surface here. And what we have done, you can see the quantum solution is missing the classical one. It's a little bit off and it's a little bit bumpy. We have developed methods to purify the state. So as I showed you, the compass needle shrinks. That's a problem. However, I know how much it shrinks by certain measurements. So I can restore that. And you can see if I restore that, the energy that I get for the solution of this transverse field Ising model is restored even at the level of 10⁻³ So this is a very promising way then to come up with quantum simulations for chemistry, say, in this method. And finally, I want to show you an example in nuclear dynamics. So nuclear dynamics, also really hard problem, right? If you think about thermonuclear fusion, this 5 nucleon problem was only very recently solved, and it required 200 mega CPU hours to do this 5 nucleon problem on some of the best supercomputers. So if you think about how to think about fission or other processes in nuclear scattering or the dynamics of neutron stars, quantum represents a much more favorable scaling of these problems. And the general idea is that in these nuclear science problems, you have a variation of the spatial degrees of freedom and the quantum degrees of freedom, right, which are spin dependent. And you can separate those in the lowest order of Feynman diagrams. and to a piece which is dependent on spin which is a piece which is independent. And again, you code that onto some quantum gates and evolve the system. And in fact, in this nuclear scattering problem, you start with a certain guess, you go ahead and evolve the quantum system, you repeat this again and again, just like the chemistry problem, till you find a stable solution. Okay, and this is real data we have run on the scattering of 2 neutrons. And shown in the upper left, these 4 colors represent the 4 terminal states, right? Here's the 0, 0, 0, 1, 1, 0, 1, 1 state of a nuclear 2-nucleon system. And you can see the dots represent what the quantum computer returned. The lines represent a direct calculation. And we did a pretty bad job, right? Because what's required here, if you look at circuit number, it says 17. We required something of order like 50 C0 gates. And that's kind of impossible to run given the coherence time we have. So you see we missed the solution by a lot. However, we now put in this randomization technique I showed you, and you can see we start to do a lot better, right? We're starting to reproduce now this shape. And then we purify the length of the compass needle. I told you we can correct for the length, and you can see it gets even better there. And finally, if we figure out what is the inaccuracy of measurement, you can see how we've taken that quantum simulation now to really show you a much better result on that nuclear scattering problem. So I wanted to mention that in the limit of noisy hardware, there are still things we can do just by being a little bit smart about where the noise is coming from, how to mitigate it, how to do this very rudimentary type of error correction. So with that, I see the time is 7:51 on your end, so I will go to my conclusion slide, right? Leaving time for questions, where I want to raise some fundamental questions in the field so that we can all collectively think about them going forward. The real question in quantum computing to me as a physicist is, how do you stabilize quantum coherence in an open many-body system, right? This is this problem of how do I make this entanglement at large scale, not have it coupled to the environment, but still be able to control it. And then once you do that, how do you measure it? How do you build a machine to treat the data for that? How do you parameterize it? How do I even describe it? I don't even have the classical means to write down that state. And then how much entanglement do I need, right? In the real world, do we really have that much entanglement? Interesting question. And finally, once you build these machines, how do you prove that they're actually better than classical ones? So these are, I think, some questions, at least for a pure scientist, that one can think about in the quantum domain. So let me stop here and pass the lectern back to our host. And again, thank you for giving me the chance to speak. Hopefully I'll learn some more Turkish next time to give you a proper ending.
Thank you so much for very nice and exciting talk you gave here. Please ask questions now by sending questions using chat button of the Zoom platform or just by raising hand. Can we now, Irfan, share in order to see everybody?
Absolutely. Yeah. Otherwise you don't see anything except the small screens. Yeah.
Please send questions or ask just by raising hand. So what about, Irfan, your last questions? You ask yourself, this is a very fundamental question, how to express quantum advantage?
Yes, so...
this is indeed very deep and problematic questions.
That's right. And I think the quantum advantage question is the following. So there's 2 pieces to it. The first question is the system that you have built truly quantum, right? Mm-hmm. And how do you measure that? So the things that I showed you were simple, right? They only had, let's say, 4 states, right? With 2 spins. So it's up, up, up, down, down, so on and so forth. Mm-hmm. When you have 2 to the n states, you cannot measure all of them, right? Because the number of measurements that you would need are 2 to the n, right? To measure all those states. So that's the first point. You cannot go ahead and measure all of these things directly. So then the natural question, Professor Ali Ikram, is, can you do a statistical sampling, right? Can I measure some parts of the system? You know, I look here, I look there, I look at this part of the system and see if quantum mechanics is there. And the question then is, how much of the system do I need to see to prove that this is truly quantum and not classical? So that is an ongoing debate. And there are 2 ways to think of this. There is something called randomized benchmarking. So you completely randomly look at the system. It will tell you in one number what the fidelity or quality of your system is. It will not tell you where the errors are, or so on and so forth. So there are methods which will decimate the information, but they will not tell you where the non-quantum pieces are. There are other methods that actually are very much inspired by these quantum circuits. like the circuits I showed you for an algorithm, you run very specific circuit sequences, and they give you a sense of how quantum your system is. So that's really the slider that we have to kind of figure out of how much you need to know to prove that you have quantum behavior, and how much of that is technologically relevant, right? What's the quality control that I need to do? I don't check, for example, some garment is produced, right? I don't check every single one, right? I check some certain number of garments, right? Or so on and so forth. So that's really the quantum version of that. The second piece is, how do you know that the algorithm is actually working the way you want to do? That's even a harder problem, right? Saying that, do you actually get the output that you're desiring? And that again thinks about maybe running some benchmark algorithms, right? We have to agree upon some quantum algorithms, just like in classical computers, and run them, see what you do.
Thank you so much. One more question, please.
Sure.
What is your forecast for future for all these things? Let's say superconducting or other possibilities in United States and in the world in general.
Good. And I have a good question in the chat as well. So I will give a short answer to your question, because it's a very dangerous one, right? So I think the following. I think in 10 years, you will have tremendous progress, no doubt. Because if you just look at the rate of problems we are solving, this is very encouraging, right? What will be different, in my mind, is what we think success looks like, right? Because there are problems that quantum systems are naturally suited to do, right? So if you can use this dynamics to your advantage, that's actually a much more natural way of using a hammer to hit a nail, rather than doing, some other carpentry task. So whereas we have started, we kind of are thinking a little bit about classical problems and how to make them quantum. One interesting way is, what are the native quantum problems, right? And see what they will solve. So I think you will get a lot of progress in 10 years. It may just look different, right, from what's there. And this universal answer, I think that's some kind of 30-year goal, right? At the end, to have this. That's maybe one way to answer this. So in the chat window, I have a question about, vacuum tubes versus modern transistors. Do you think all types of qubits suggested today will be obsolete in a few decades, or will there be a best friend? A fantastic question, right? So I don't think all types of qubits will be obsolete. There's two things I think that will need to happen if you look back at the vacuum tube. Number one, we invented at some point the integrated circuit, right? The integrated circuit allows you to put lots of these things at small scale together. We don't really have the integrated circuit for any of these quantum platforms, right? So the first one that will get the integrated circuit, I think, will have a lot of progress, because then the other ones become not so easy to scale. So that's sort of the first question. So I don't think necessarily they will all become obsolete. The ones that are integrable into a circuit will be better. The other thing that I didn't talk about in this presentation is, again, this open versus closed quantum system. In a modern classical processor, you have different pieces. There's memory, there's cache, right? There's a processor. There's all sorts of different things that are there. And you may need the quantum equivalent of that. So for example, in photons, you may make a great memory. They will hold your quantum information for a long period of time. That's your RAM, right? Where you go ahead and store information, or a lookup table. Whereas electrons have very fast dynamics. So that's good to make a processor. You want to do lots of flops quickly. So the idea of having these hybrid quantum systems is yet another layer of challenge on top of this, right? How to actually make these different quantum systems talk to each other. But I think that's also a very interesting prospect. This means we need awesome transducers too. Absolutely. Absolutely. One of the things we did not talk about, Sarhat, is that how do you transmit quantum information, right? For example, you have one computer in one place, the other place. Right now, you're using the internet, right? You're sending we're talking to you right now from California through this. How do you do that across quantum mechanics? There are no wires that will do that. So how to actually transmit those things is very important. A randomizer from Duruk makes results. Do you have time, Professor Ali Kram, or do we have to stop exactly?
Yes.
Okay, I'm happy to answer the question.
No problem with time. Please.
Good.
Decide yourself, yeah.
Yeah, so a randomizer makes results better, as I understand, and the cost is that I lose information, right? I want to ask how much that lost information matters, or do they stack, and as a result, a very huge mistake? That's a great question, right? So again, this randomization is useful in certain limits, right? So the information we are losing, you're absolutely right, is what was that error channel. But the stacking is in a more favorable way. So in certain cases, it's beneficial. In other cases, it's not. So let me explain which cases are which very quickly. when your quantum solution produces, your quantum algorithm produces a state which points on the equator, which is a superposition, versus the pole, you get a different result from randomization. Right? When it is subject to a lot of error, the randomization helps. When it's not subject to error, then the randomization doesn't help. In fact, it harms you a little bit. And a perfect example of that is the quantum Fourier transform. When you take the Fourier transform of a singular state, you get all the different weights. That's what Fourier transform does, right? If you have fixed frequency, a sharp time domain, you get a lot of frequency components. And the opposite is the same. If your input state is many components, you get a singular output. So randomized compiling works great when you have all of these components at the output, right? And it's not so great, you lose something in the other limit. So that's how you balance that. From Achar says, in Josephson junction quantum circuits, is normal diffusion hold or anomalous diffusion hold? Would the Levy flight instead be a Brownian? Great. So the Josephson junction transport that we're looking at basically has two flavors. If you take this junction with two superconducting electrodes and one barrier, at low energy, the charge carriers are only Cooper pairs, right? So there is no resistance. There is no scattering at zero frequency for that. This is where you feel the element is an inductor, right? And in fact, you have this kinetic inductance associated with that motion. There's a time lag, right? Because it takes time for one Cooper pair to go to the other one. So in this case, there is no anomalous diffusion or Brownian motion, et cetera. These are things which are referring to the time when you break Cooper pairs, right? And you have dissipative transport. So those quasi-particles are actually very bad for quantum computation. We would like to get rid of all of them. And in fact, they are created by cosmic rays. So cosmic rays come in, they create these quasi-particles, and it's a real mess, okay? So we would like to get rid of all of this diffusion. So you're right, these diffusion effects are bad, and we want to get rid of them. Okay. Professor Getz, thank you. So.
Okay, thank you so much. Perhaps I would like to talk.
Good. Perhaps I can answer. Let me just answer this last one. So that's here.
Yeah, last one. Yeah.
From Iman. I would like to ask about achievements for improving coherence time in superconducting qubits. Good. So there are two approaches to this. I wrote recently a paper which has come out in Nature Reviews for Materials. So that may be an interesting reference to your question because it's a 17-page answer to that question. But the short answer to this is you can make materials better by cleaning up surfaces and interfaces, or you can make circuits that are more complicated. I showed you a single junction circuit. If you use multiple junctions, then you can get a more complex encoding information. So those are two ways.
So thank you so much once again, Irfan, for this very exciting and comprehensive talk. Will you please give your final, perhaps, remarks?
Sure, I would be happy to.
And close our session.
So first of all, let me thank you and the team for inviting me.
That was a great pleasure for us.
It's a pleasure and honor for me, right, to join this audience. I wish we could do it in a more interactive method, hopefully soon, right? This virus we will be rid of this, right? And we can have proper meetings where I can meet all of you and answer your questions in real time. I think the vision going forward is one of a very exciting one and an encouraging one in terms of inclusivity of a broad audience and broad spectrum of thought, both in terms of people, the type of scientists we bring into this and their mindset. So do not be shy to ask questions and to engage in this topic because we have not figured it out at all, right? There are a lot of places to plug in. We really need different viewpoints, mathematicians, engineers, men, women, everyone to come into this, right? To think about this. And I think it's a real tremendous moment for us to kind of reset the fields, right? Sometimes in science, fields that have been around for a long time, they have a particular mindset and a particular population. We are hitting it from ground zero, setting it again. So please take this as a word of encouragement to plug in, to think, and know that there are heavy contributions to be made from all of you. So maybe that's my final remark.
Thank you so much. So thank you everybody for participating in this very nice talk. So we can stop here. So
yes.
Bye.
Bye-bye.